So kernel trick. So in support vector machines, there's a few hyperparameters that we can deal with. And so just kind of looking real quick at scikit-learn's SVC, which is support vector machines in scikit-learn. But you can see there's a whole bunch of extra things. So you can actually define like the C right here, like I mentioned, the penalty term for the error, right? So note that you can basically change this guy. You can also do things like change the kernel, which we'll talk about in a second. And you can change things like gamma and stuff, which we'll also talk about, like how these are. But these are mostly, for the most part, hyperparameters. This is kind of decides how the support vector machine learns and defines what what's it called? What that boundary and classifier is going to look like. So the kernel trick is kind of an interesting idea. So basically it's like when we have a hard problem, we cheat and say, well, this is too hard. Let's go into a higher dimension to figure it out. So like a really easy way to define this, let me see if I have a little diagram. No, okay. A really easy one you can think of it is that if we have a problem where we have just a single line, right? And let's say we have a blue point here, a blue point here, and a red point. Is there any line that you can draw that will separate the red from the blue? Any straight line? Yeah, it's not a trick question, no. Like, there's no way you can do it. You could try, right? But you won't be able to, right? So no matter what kind of line I draw, I'll never be able to completely separate these points from, right? Any one line. So one thing we do is say, well, okay, that kind of stinks. But what if we could like, let's just say we nudge the red point just like up here. Okay, just like raise it up to here. And so the red point instead of here is just we move it up. Can we draw a straight line now to separate them? Yeah. Yeah, hopefully it doesn't feel like Blue's Clues or something. Like, can we do it now? Yeah, of course we can. So you can imagine we draw a line like, you know, just going right through. So, oh, cool, straight line, easy pie, right? And all we did was just kind of cheat and say, oh, we're just gonna nudge you up a little bit. So the red point's just a little bit higher than everything else. And then we can draw that line through here. That is what the kernel trick is doing. Basically, we're cheating. We're saying, hey, like this is a really hard problem and I don't know if we can solve it. Let's just go ahead and raise into, essentially, this was only a one-dimensional problem. Essentially, they're all on one line. And we made it into a 2D problem. We raised it up, say, okay, let's move the red point here, and now it exists in X, Y, so we can split it off. One thing that I think kind of goes into, what's another way we could have solved this original problem without trying to cheat? And this time you don't have to draw a straight line, and that's the key part. So you don't have to draw a straight line. What could we do?
A parabola?
Yeah, right, could like do something like this, right? Yeah, and that's probably like honestly what most people would think. Like, yeah, we're just gonna draw a funky function to kind of just draw around it. Like, if you ask the kid, can you draw a line to separate it? They probably would be like, okay, and just like that's how you would do it. What's cool is that the way drawing this like this, which actually can be really hard to figure out, like what kind of function should be drawn to make this fit, to separate these two together, like think in general, and me moving that red point. It's literally the same problem. It turns out they're equivalent to each other. So this is why it's called the kernel trick. And the idea of the kernel is basically that you're using it, the kernel essentially is the idea of raising it into a new dimension, basically give it some extra features, and that allows us to separate it. And the real reason why this happens is because in higher dimensions, you have more space. Like this is kind of a weird thing to say, but basically in higher dimensions, you just have more degrees of freedom to move around. So it's basically you're more likely to be able to actually make a single line cut, like a single straight line cut to go through everything. So here's one, for example, for the curriculum, but I consider a line with no good cut extended to parabola. So that's kind of like what Tara just said, is like, you know, oh, we could just make it into a parabola. So like equivalent to here, like if we had 2 dimensions, you can see, oh, well, there is no like straight line I can do, right? There's no straight line I can do to separate this. One, like Tara had said, what we could do is draw something like, oh, you could draw like a parabola like this, right? Oops, that's not, that's a straight line. Draw like this. We can draw a parabola like this, right? So that allows us to separate them out, right? But the thing is, like, you know, like what kind of parabola do we need? Like that's going to be kind of a frustrating part, but we could do that way, right? So what we can do instead is like, well, let me just raise this up in the power and do this. Another way you can think about this, which before I show the powers, is we can think of it like saying, okay, we have not just x and y, so some line on x, oops. So right now, like a line on x would just be like this, right? Just horizontal. I'm sorry, a line on y would just be like y equals 5, right? And this is like y equals 4, right? So you can imagine drawing straight lines. So this is just the using just y, or we could use just x, making vertical lines. None of these would work very well. We can do all that together and say, okay, let me just go ahead and try to draw x and y together. So x, like something with x and y together would just be like a straight line in some way. But what we can do is like, well, what if we said instead of just doing x and y, so either x equals something, y equals something, or x equal, like x times something, let's just call it like a equals y times b, like doing something like this. Like, well, what if we said we had y x squared, xy, y squared? And then if we do that, like, well, that means we have a lot more options now. We have a lot more ability to say, okay, well, instead of just doing like, you know, y equals x or y equals like 3, we can do things like, well, if we do like y equals x plus x squared, or we can even do like x plus x squared plus xy, okay, or plus y squared or something like that. So we can make all these different combinations to make a really complicated function. And the idea here is like we can build this up, and for example, the simple one would just be like, oh, something like y equals negative, I don't know, let's say negative like 1/2 times x squared, right? So we can see here like plus, I don't know, plus 3. So that'd be something like this. That would make that parabola in there. So we're using all the pieces, not just integers, not just x, but also x squared. We could use y squared and stuff like that. Does it make sense? Okay. All right, I see some puzzled faces, so maybe that wasn't the best way to kind of do this. How do I try to phrase this in a good way that's like trying to motivate a little bit. When we build a straight line, basically how can we, give me an equation for a straight line? Any straight line, either specific or in general.
Two x plus 3.
No. Okay, so y equals 2x plus 3. All right, and then Tara, you had one too. Go ahead and say yours.
I just said y equals x.
Y equals x, that's also a straight line, right? Anyone else? What's the general form for any straight line?
Y equals mx plus b.
Y equals mx plus b, good, right? So if we put any numbers we put for m, any numbers we put for b, that will always be a straight line in 2 dimensions, right? So if you put, you know, for example, if I put b equals 0, that is y equals x. If I put m is equal to 2, b equals 3, we got y equals 2x plus 3. Cool, right? If I put m equals 0, and we put like b to like 3, well, then y equals 3. Is that a straight line? Yeah, right? There's actually even a more subtle one too that we could do. And usually your math teachers wouldn't do this, right? But you could actually say, okay, c times y equals mx plus b. So then we can say, oh, if we set everything else to like, if we set y equal to 0, we could do something like, oh, or let's say, yeah, y equals to 0, and this is like b equals, I don't know, 3. We could do like, oh, 0 equals, let's say m is 1, x plus 3, or just saying x equals minus 3. So you can see that you can build up all these different equations. This will always be a straight line. But if you want any curviness to it, you got to add some extra factor in it. One way you can do that is like, okay, not just y, x, and just a number. We can also say, well, what if we have an x squared term in there? Well, then we know if you remember back in like algebra 2 or whatever you do like in college or high school, you can say y equals x squared plus, you know, x plus, you know, 1, and that will be a parabola. In fact, any term where you do y equals ax squared plus bx plus c, right? Looks familiar. If you have something like this, you can build any parabola you want, right? And if you wanted to have some fun with it, you could also, like I said, have it multiplied for the y side as well. And that just allows you to get rid of y if you wanted to. But that should also give you some kind of parabola. And that's what this idea here is. We're extending it out saying, well, okay, instead of having just x and y by itself, we can have x, y, or sorry, x squared, x times y, that's a fun one, or y squared. So we can combine them in however we want and build whatever kind of weird function we want to make that perfect, you know, kind of like weird looking function to separate them out. And what's kind of cool about that, like that, I think for the most part, that makes sense. Like, oh, we can make it more complicated. We have more features to play around with. Think of this as like linear regression, or when we extended linear regression to interactions and polynomials, that's what we're doing, right? What's cool about this is that this is literally the same thing as just saying, well, what if we transform the actual data and move it into, you know, higher dimension, in this case, like a 5-dimensional space, and say, hey, let's separate this out. Turns out these are equivalent. So sometimes it makes sense to do this, but this turns out I don't know. I think this is kind of hard to like figure out exactly how to do this. If you can just say, hey, what if we move the data points out of like this part and make one simple cut, that actually makes it really nice and easy. So one way you can kind of view this too is you can imagine, say, okay, what if we take these data points and say everything in this point is going to be raised up by a certain level. So you can imagine, like, you know, saying, okay, like this part is going to be raised up in a 3rd dimension. So we have X and Y and we're raising it up. So if you imagine, like, I'm trying to do the best here. This is from the curriculum, by the way. But if you imagine like looking down on this point and then I moved those blue points up, if I look down at Z, right, and I look down at this like blue points and red points, it would look literally like this. And the only difference is that the blue points are raised up. And that means I can make a nice clean cut just right through. And it turns out those are the same exact thing. You can think of it in either way. Okay. Does that make sense to people?
So Victor, in this case, are we only changing the dimension of the blue points, or it applies to both? I'm just having trouble like understanding.
Oh yeah. Yeah, so this is where it's a little, to be honest, I think it's not that we're necessarily changing the blue points. What we're doing is kind of like, imagine this is like on a piece of paper, or like a better yet, like a blanket. And the blue points are like little dots on the blanket. And so we can't move the dots off the blanket, but what we can do is like take the blanket and like pull it up. And we can pull that upward on that blanket, and all the blue points are gonna stay exactly on the blanket. And then we just make one clean cut. Or what we could do equivalently is try to cut around it, you know, and it would be the same thing as if we raised it up and then cut it. And that's what we're doing essentially. Does that make sense?
Yeah, I guess like I don't understand yet how we know like
where to
how
pull it,
to
right?
raise the blanket so it's only the blue points. Are we gonna get into that, or I just don't really like, I understand what you're saying, but like I don't know.
No, perfect. That's actually Tara, you're like my perfect like segue person, because I feel like you read like the next question, exactly what we're going to talk about next. So the next question comes into, how do we know how to pull this blanket? How do we know what to cut? Like you can imagine the same issue here. It's like, how do we know what combination of x, y, x squared, x, y, and y squared? Turns out that's actually a really tough thing, right? Imagine like trying to find a linear regression problem with many interactions. That was a really tough thing for you to do with polynomial regression. So it turns out this can actually be a lot easier. And this tends to be a lot easier because we kind of can build things around it, and then we can transform it later. So this actually leads us into like this kernel discussion. So remember, a kernel basically is really a way to split the data into different parts. So we say, okay, this different part. So a really common way is something called an RBF, or a radius basis function. Or I said kernel here, that's funny. But basically the same thing, kernel. But like we're basically using a certain type of function, and this will allow us to build anything we want to separate them out. It turns out we can actually modify this radial basis function, and it is a function. It's basically a way we're pulling up on the blanket, because I obviously know that we can't pull the blanket in certain ways. Like we can't pull the blanket and tear it, otherwise we're already making the cut. So we have to do this smoothly. And that's what those RBF guarantees, is that we can always do it smoothly. And we can just, you know, have like maybe some volunteers like, oh, there's this weird blue point. Can you hold this point? It's like, okay, you hold this point. It's like, oh, can you pull on this point? And then we're just gonna make one solid cut all the way through. That's essentially what this RBF will allow us to do. Okay, so it kind of helps a little bit to say like what an RBF is. Let's see, we have about 13 minutes. Okay, we can kind of get through this. So I'm gonna just kind of go through a part of it of like what this looks like. So if you remember way back, like I think like way back when we did statistical distributions, and I was talking about how to make a KDE. So we know KDEs now, right? We like KDEs, right? This is essentially what we're doing, the same thing, except we're doing a different kind of function called a radial basis versus a Gaussian. And essentially what we do, we make this radial basis function like a Gaussian, and you say, okay, there's this certain equation. We don't need to know what it is, but say, okay, we can center at this point right here. And essentially what is it's highest at this one point. So imagine this is the center, and it kind of goes off into infinity, approaching 0 as it goes off to the side. And we do that for each point right here. So what's kind of cool about that is like when we have these different points, we can actually define this radial basis function. So this is easy enough. It's like, okay, we can basically make a red one, we can make a blue one, and then what we can do, let's see if I actually show you right here. That's not what I want to show. It's here. Well, okay, what we can do next is say, well, everything that's red, just multiply by -1. And what that will be equivalent to is just saying, oh, let's just make a radial basis function like this. And say, okay, all the points that are on this point right here, you're going to be moved down here, and all these points over here, they'll move up here. But now we have to say which one's blue and which one's red, so we can combine them together, and that's what this represents. It's like we can combine them all together. Now, what this will actually look like, since I'm going to flip one over, what this will look like if I were to draw it all together, we'll have the blue point that was kind of like this, and then the red point will kind of go like this. So you can imagine like I'm combining that red and blue together. Does that make sense to people? Okay, so remember, I'm just kind of flipping over that -1 for the red. And then I can say, okay, all the points go up here, go to here, and then this blue point will go right here. Same thing with this red point will go down here. This red point will go here. This point will go here. And then I say, okay, make a cut, and I'll just cut it right across here. And then that means I have all the red ones on the bottom, all the blue ones on top. And note, I can kind of adjust that like cut wherever I want. So that's how you do it with 2 points. And this is based on the fact that I can make this radial basis function, kind of like a Gaussian in some ways, not really, but we can make these centered on each point. So if I have multiple points, so instead of just 2 points, I can have something like, 3 different points like this. I can have this blue right here, this blue right here, having these little extra bumps. So note that these are the same kind of function, this RBF. So each one of these points have their own little RBF, but they're centered at different areas. And then what I can do, I can combine them together. In this case, I can add up the blue together, and I can add up even the red together. If I wanted to, I could multiply this by -1 and have like a negative looking function where it goes down like I showed you before. I think I do. Did I show that here? No, I did not. Okay, so the idea here is like, well, okay, if I had something similar, what I could do is draw out each of those points, kind of saying, okay, here's my blue one. Here's my other blue one. Oops, that's not a great one. I'm trying to make it as best as possible, but quickly. Here's my red one. So this is going to be kind of like this. You can imagine my red here. Here. And note that like when I'm drawing these curves, they're not perfect. They're supposed to be a very specific shape, right? And then I combine them. It's like, okay, combine them all together. And I can say, okay, well, what I'll have instead, let me see if I do this in pink. That way it stands out a little bit better. I'll have like going from here, and I'll have kind of like this bump going on here, then another bump, and then I'm going to have this negative, everything that's red. It's like, okay, that's going to be like the negative of that. And then I'll have another bump right here, and then another bump right here and going through. And then all of these points will get mapped to somewhere on that curvy line, on that pink line. Does that make sense? Okay, and then once they're all mapped on there, I can just make that clean cut, and I know where all the points are. Does that make sense? Cool. Any questions, any clarifications I shouldn't help out with? Okay, so that is how we would do this in 2 dimensions, right? Or 1 dimension expanding it to 2 dimensions. And kind of going off what Tara was saying, like, it's like, well, how do we know what to do? Essentially, this function can be predetermined. It's called the RBF. So we can say, oh, using this RBF function, you apply it to this specific point, and now all of a sudden you get this nice curve, and we can go ahead and separate them out. Okay. Cool. So a 3-dimensional way of looking at this. So you can imagine instead of saying like, okay, like what's this like 2D? What if you had 3 dimensions or higher dimensions? You can make an RBF in multiple dimensions. So you can see here is that this in this red right here is kind of like that blanket essentially. And the shape that that blanket is doing is the RBF essentially. It's like, oh, it's already a predetermined shape, and you can combine them. You basically make one for every single point or a collection of points, your training data, and say, okay, this is how I can build up this, what's it called? this RBF and combine it into one big RBF, kind of like how you would combine like multiple Gaussians together or something like that. Okay, and then once you have this all to combine, you can just draw your threshold and decide where you cut it at. And depending where your cut is maybe the better classification or your SVM. And that will actually map on here if you imagine drawing here, and you can see like how it kind of got this little extra bumps and stuff like this. It'll look something like, okay, like I'm not gonna do it perfectly here, but you can imagine because it's gonna cut around here, it's gonna have these extra little like parts. And essentially that thing that mapped down will be your actual boundary. And that's how we can draw around it. Okay. Does that make sense to people? Thumbs up if that sounds good. Sideways if you're like, I don't know. Okay, still see some sideways. Okay. The main thing here is hopefully the analogy with like pulling on the blanket kind of deal makes more sense where you can make that cut. And that main idea here is we can decide where to pull on the blanket by looking at each individual point, our training data, and say, oh, okay, you're gonna pull up by this much. Oh, you're gonna pull up by this much. Oh, you're gonna pull up by this much. And that allows us to kind of form this radial basis function together. Okay. Now, one thing to do is that this is another hyperparameter, gamma. Gamma tells us basically how hard do we pull up on any of those points. So essentially, do we make it a really skinny mountain or do we make it a really fat mountain? So just kind of know, I don't know if I have no, I don't have an example of this, but basically allows us to say, okay, if you have a gamma that allows it to, what's it called? If you have a very big gamma, it means you're gonna have a very, you're gonna pull it really far up, which means it's gonna make really, really skinny points, which means you're gonna tend to have overfitting. Does that make sense? Essentially, it's like you're able to separate this out because you're able to just pull that one apart and you're just gonna have a really skinny mountain. Versus if you had something that is a larger or a smaller gamma, you're gonna have like a larger part where it's gonna kind of like you almost grabbing a whole bunch and pulling it up, and it's gonna grab a few points that are nearby. So that's where that gamma kind of comes in play in this analogy. Okay.
So it doesn't matter how high you pull the points up, it only matters where you make the cut.
Right. Well, I mean, in some ways it does matter how high you're pulling it up because you're going to make the cut there. And so it's going to be, if all the points get pulled up higher, it's going to be easier to make that cut, right?
Mm-hmm.
Yeah. So in reality, you're probably not going to make the perfect cut. Like you could technically, that's where that gamma comes in. You could technically make that gamma bigger, and you're going to pull up all those points really high up, even though it's just one of them. And then you can make a cut and then you'll always get it. But then you'll get these like really weird, like what you'll see a lot of time with high gamma is you'll see something that maps down that looks like this, where you have like these 2 points circled and then like this point's circled. And you'll kind of have these weird, like almost like weird blobs that are almost like why don't they just combine that together? And it's because they're all being pulled up individually versus this one, it's like being pulled up all together. So, and that's because they're being pulled up all together because there's more points close by.
So you'd have like pinnacles rather than a mountain.
That's right. Yeah, you kind of have these weird peaks kind of coming up.
Yeah.
Yeah, good. All right. So kind of showing you like, it's like, okay, like you can see what this maybe, hopefully this kind of helps with a little bit of analogy of like why this works. And when I say analogy, I mean like that is literally what's going on. It's just kind of like hard to picture in multiple dimensions. Like if you imagine your data set is like 3-dimensional or 4-dimensional, how do you visualize this? It's the same concept. It's just that it's hard for us to actually see. But what this looks like, and this is coming from this example here, you can see a little bit, and I'm just going to run this code since we're a little low on time, using the iris data again. And we'll go ahead and plot this out with us different support vector machines with our different parameters. So this is just going through a bunch of different C's to see different hyperparameters. And I'll go ahead and plot these parts out. And you can see here is that these are each different classifiers. And you can see like this dark red and this dark red, or dark blue and this dark red. Hopefully no one's colorblind. You can see that okay. But you can see here is like this red is a very low gamma, right? Or no, it's not low gamma. Yeah, this is a relatively low gamma. So we have very like fat, we don't have high peaks, we have like this fat mountain. And you can kind of see, imagine this darker color in blue in the background here. It's kind of like how high up it's being raised or how high it's being like lowered. And so you can imagine like, okay, like this right here is being raised up. You can see it catches some red points. And you can see as we kind of travel closer to a higher gamma, but keeping C the same, you get more of these more extreme points. So you can see here, this is getting raised up a lot differently than its surrounding. And then if you look closely on here, I don't know how well you can actually see this, but you can kind of see that there's like this blue, and it's because they're being picked up essentially on those specific points. So you can imagine, like Andrew was saying, like you have these like peaks that are kind of sticking out, like these pinnacles that are sticking out on the side, especially like these red ones right here. You can see how it's very red right here because there's basically being picked up really high up. So that's what happens when you have a high gamma. And you can see a little bit, I think these ones are like lower. I can't actually see this well. Let's see here. So this going downward, this is like essentially higher and higher C. So remember, our C basically is saying, what do we care more, the margin or the classification? So you can see as we kind of go further and further into a lower C here, we care less and less about the actual classification and more about the margin itself. So you can see at the beginning here, it's kind of like getting most of these points, but then as we get over here, it's looking more about like, what's the margin, even though it's kind of missing those points. So you can kind of see a little bit, and this is where, like, if you remember, I think the curriculum talks about grid search. This is like essentially grid search. It's literally looking at the grid of hyperparameters and saying, what is the best thing for it to figure it out? And then this is just from scikit-learn, just showing the validation accuracy, saying the better the accuracy, the lighter the color. So you can see here, it's a really good accuracy. And you can see it's not going to be at, you know, extreme values. It's going to be somewhere a mix between a decent gamma and a decent size C. Okay.
So on those other pictures, it would kind of be the one in the middle is the best model?
Yeah, this one in the middle looks about right. And that's probably makes sense here. You can see the best models are just about on the average right here on about, looks like what, 10 and 0.1. So probably, this is about, where's 10? This is 10 right now, this is 1. Oh, they don't have 10 on here. This is 100 for C and then 0.1 for gamma. But the idea here is like, yeah, this would probably be a little bit better than the rest of these. Okay. Now it's a little hard to tell with like, at least for the margin error, it's a little harder for us to like quantify that just visually, just because we don't have a firm part, but you can kind of see how well it classifies. These ones you can see classify pretty much every point pretty well, but you can probably tell that this is overfitting. Like this is not a good situation here. Versus this one, oh, this seems very moderate. It seems closer to like what blue really is doing. And then this one, I don't know how well to explain this one. This one's caring a lot about the margin and nothing else essentially. Okay. Cool. Any last questions about kind of see how this goes through? Okay. Cool. Yeah. And so again, hopefully that analogy kind of helps you. Like if you can now look at this picture and kind of picture like how the sheet's kind of getting moved up a little bit, I think hopefully that kind of adds a little bit more. In my opinion, that's more intuitive than saying, sometimes people talk about like the gamma or other ways of the kernel saying more on the two-dimensional space without thinking about it being raised up or raised down. But I think if you think of it like being raised up or raised down, or just lowered down, it's a little bit easier to kind of visualize what's going on. Okay. Cool. All right. So I'll go stop the recording here if you guys are good with that.